Hello. So today I'm going to be talking about UNet. So the UNet is a deep learning architecture used for image segmentation problems. When it was released, it was particularly released as a solution for biomedical segmentation tasks, but it's been come to used for virtually any task. In fact, if you go to Kaggle, you will find it to be the go-to architecture for any segmentation problem. And even if you are researching on segmentation problems in other domains, you will probably come across UNet. I think so. The UNet is currently the most cited paper uh, in biomedical deep learning, and we'll see that this paper was a little bit ahead of its time. So it came out in on May 2015, and the deep residual paper by Microsoft came out on December 2015. And we'll see that the UNet uses something like the skip connections, but not exactly. So the UNet has particularly been uh, very useful because unlike classification problems where we use hundreds and hundreds of layers, UNet provides a very compact architecture with limited number of parameters to do our task. So let's take a look at what image segmentation tasks look like, and why a network needs to learn a lot more about the classes than for normal classification. So here are some examples. So this is actually a problem that I am currently working on. So here you can see that these are like images of the brain, and here the network has segmented the different subclasses of tumors in different colors. So this is like the whole tumor, and these are the subparts of the tumor. And then this is a problem about nucleus segmentation. It's distinguished between the nucleus and the background. And of course, self-driving cars use image segmentation for awareness about the environment, and you get the idea. So unlike regular classification where we classify an entire image as, let's say, having a tumor or not a tumor, here we are classifying every single pixel as to what class it belongs to. So it's not just enough to kind of know some feature and say if a tumor is present or not. We need to know exactly the shape, and we need to know all the intricate properties about how this object behaves and the shapes and the forms it takes to exactly know which pixels belong to that. So this kind of task requires the network to have a considerably more in-depth understanding about the object. So let's take a look at the UNet architecture. Or first, actually, let's look at how segmentation tasks were approached before the UNet came. So back in 2012, we started using convolution networks for classification, and by 2014 we started to adapt them for segmentation tasks. So this would be your regular classification network. You have a bunch of convolution networks, and then finally you have fully connected networks, and you get an output. So people tried to modify this. So since we want to output, as you can see, we want to output another image, a map of the input with our labels. We don't want to collapse it into a vector. So what people did is that they replaced these fully connected layers with fully convolutional layers, and whatever they got at the output, they would just upsample it to the same resolution of the image, and they try to use this as a segmentation mask. But as you can imagine, that because we have kind of compressed this image so much and it's gone through so much processing, and also the max pools have kind of thrown away some information, just doing an upsampling will not really give us the kind of fine resolution that we want. It's going to be very coarse, and it's not really going to be very accurate, right? We're taking this small let's say 20 by 20 image, and now we are blowing it up to like 512 by 512. It's not going to look very good. Maybe that was a little bit of an exaggeration, but you get the idea, right? It's just regular upsampling is not going to work very well. So what the UNet does, and there were many approaches before the UNet, but let's just skip to the UNet. So what the UNet does is that you can see that the first pathway of it looks very similar to this part, right? And then instead of just directly upsampling, it has another pathway through which it gradually builds upon uh, the upsampling procedure. So instead of just directly upsampling, we are kind of now learning the best way that this compressed image should be upsampled, and we're using convolution filters for that. So this was a pretty good idea, even though there were other papers that kind of used this. So what are these arrows that are kind of pointing through? So these, if you look at any architecture, you would assume that these are like skip connections, but these are actually concatenation connections. So normally for skip connections, you do like a sum. So you just add two activation maps and you get another map of the same direction. Well, in concatenation, suppose you have one activation map of depth d1 and another one of depth d2, then you actually take d1 and you stick it on to d2, right? So you would like you kind of you kind of stick it on, you don't add it. So the kind of final block that you get is a combination of d1 and d2, right? You've not lost any information. It has both of them. uh, so so now let's look at the architecture. So here you have an input image which goes through some convolutions. Then this is downsampled, usually by using max pooling. Then this goes through some more convolutions. It's downsampled again, goes through some convolutions, and so on until we reach the deepest layer. Now we upsample this. So suppose the height over here, or the height and width were some h and w, and we downsample it by half, so we get h by 2 and w by 2. And so we upsample this by half, so we get h and w back, and then we concatenate both of these. So as you can see that we have the blue kind of box, or the features coming from this one, and the white ones are coming from this one, and they are kind of stuck or joined together like this, as I showed you before. It's kind of like appending two lists instead of adding them. And then this jointly goes through some more convolutions. Once again, it's upsampled, it's joined back with this layer, and you get the idea, right? So let's look at kind of what happens to the sizes. And this was back in 2014, so uh, you know current practices may be slightly different. So over here, the input image of 572 by 572, when it goes through convolution, it becomes 570 by 570 because they do not pad it, and so that's why it kind of decreases by 2 after every convolution. And max pooling halves it, as we already know. And so you can see that the number of filters or the features are doubling at every step. And over here, from they take it from 1024 to 512, then they concatenate both of these 512s. And over here, the height and width over here is 28 by 28. So when they upsample this, it becomes 56 by 56, and this is 64. So they, as you can see, they copy and crop, so they kind of just leave out the pixels at the end. Another convention would be to pad this to make it 64, but that's like a choice of yours. And then this is done, so it goes from 1024 to 512, then 256, then these two 256 ones are concatenated, and so on. Now usually people use some bilinear upsampling or transpose convolution over here. It depends on your memory requirements. Bilinear upsampling is a less computationally intensive operation than transpose convolution, but the upside is that in transpose convolution you actually learn the upsampling process also. So as you can see, the number of filters as we go down is increasing and increasing. So that means that it's becoming very, very good at detecting more and more features. One important thing to know is that we're losing information as we go down. So obviously through the max pool, we lose some information, but even through convolutions, because convolutions are throwing away information from the raw input to repurpose them into meaningful features. Right, that's what we also see in classification networks, where we, by the last layers, a lot of the input has been thrown away, and it's just like the raw features that the CNN wants to make the prediction, or just the relevant information. But in segmentation, we kind of want those low level features also, because those are essential to reconstructing the image. So when we kind of downsample this, we throw away about half the information, and then when we upsample, we kind of get this back, so that we can see these features in the perspective of these features, these details. We can see them together, right? So we're not really losing out this information as we would in this case. We kind of still get all these features back by concatenating them to our outputs as we go up these layers. So as you may already know, the first few layers of a convolution network capture very small semantic information and lower level features. And as you go on and on, those features become larger and larger. But as we are throwing away information, the CNN only knows an approximate location about where those features are. So let's look at an example. So here you have a self-driving car task, and you can see that by the time that you take that input image and you get it all the way down here, it's become much smaller, and it can detect that the car is present, but it does it so in a very coarse way, right? So it knows that the car is kind of approximately present over here, because it's kind of looked at these features around, and it knows that somewhere around here there's a car. Similarly for people, right, it kind of knows that, all right, in a very coarse way, that all right, around here I've detected a person. But for it to distinguish exactly between the boundaries of two objects, it needs kind of the lower level semantic information that it captured earlier. So this could be like what it captured on the first layer. So it detected small edges and small differences. And so if you were just looking at this very coarse output, we would just get a very approximate sense about where the objects are, kind of like here, right? We do get that the cat is present here, but it's not very fine, right? Because this lower level information about the edges and exactly the presence of eyes, these things are kind of missing. So when we fuse these two together, we are able to look at kind of this small semantic information in the context of these global features, and we are able to much more exactly determine what class each pixel belongs. So like the starting convolution layers have a lot of information about the semantics, while the deeper layers have a lot more information about the features. So our objective is to kind of fuse the semantics, the lower level semantics, with the higher level features. So let's try to understand how exactly this is happening in the UNet. And this is, the most important thing to understand, because remember, we already had this stuff before. The innovation was, how do you upsample these features, combining them with the lower level semantics that we've captured into this really dense prediction mask. So I'm going to quickly try and go through this. So let's say that you have some activation block, and you convolve it with one filter, and as you know, it produces a 2D map. The added receptive field size gives or allows you to get critical information about the feature that you're trying to detect. So it's important to have an idea about what like an activation map may look like. So let's say I convolve this filter with this image, right? So where this feature and the feature that it's looking for exactly coincide, we're going to do a dot product, and this dot product is going to come out very high. So like somewhere over here, this is going to be like a really high number, like 10, and even over here we're going to get a 10, and in all the other places we're going to get like very tiny numbers, or negative numbers or whatever, because of there will be some overlap between all these places. But it's important to recognize that this dot this dot represents the represents how much the feature that this filter is looking for is present in this kind of 3 by 3 grid centered around this dot. Okay, so I have another illustration of this. So right, so let's say we want to detect faces, and so we have 3 filters over here, 3 different filters. So this looks for eyes, nose, and mouth. And when we kind of convolve these together, you can see that the eyes are detected over here. So this lights up, the nose lights up, and the mouth lights up. And we have many more filters like this. So we finally stack all of these together in a block of features. And then when you want to detect a face, we want kind of all these elements one below the other. So if this block is this block, kind of a list of all the features, and these filters happen to be in the IJK position, their activation maps are here, then our filter that looks for faces is going to have high activations in these corresponding blocks. So like if it wants eyes to be on the top, so like at the ith position, the filter is going to have like high activations on the top, and if it wants nose to be just below that, at the jth position, it's going to have like in the mid range, it's going to want a nose somewhere around here. So it's going to do a dot product once again, and its output will also be like a 2 by 2 feature map, and this number will correspond to how much a face is present in some local region. So as you can imagine, that different shapes of eyes, and because we are also doing max pool to make our convolutions invariant to small changes, different kind of shapes of eyes will still produce a high activation for the eye detector, right? And similarly for these things, right? So even though there is some slight variation, because this is just outputting a score, we are going to lose what exactly that variation was, right? And even over here, like if the eyes are somebody's eyes are slightly tilted, or the nose is slightly to the right, this face detector, because we've done a max pool, is still going to output a high number over here, like 10, just as it did before. So how would we kind of distinguish when there's a slight change or where there are subtle differences? And the dot product makes this especially confusing, because remember, the dot product is not a unique. So what do I mean by this? Okay, so let's say that this filter over here kind of gives a score of 4 to the eyes if the eyes are perfect, 4 to the nose, and 2 to the mouth. Okay, just as an example. Now let's say that there is no mouth, right? So this gets 4 plus 4, it gets an 8, right? It gets an 8. Okay, it's not there. Now let's say there's another scenario where the eyes are perfect, the mouth is perfect, but the nose is kind of only half the nose activations are present, right? So this will also get an 8. So how do you distinguish between these two cases? Because if you have a dot v is equals to like some number like 5, and v is a fixed vector, it's a filter, then this is not unique, right? There could be many a's that give you this 5. So there is an inherent ambiguity into exactly the semantic information present at this level. So this is why it is kind of critical to retain this, because this will kind of fill in all the gaps that this is missing out on. So as I said earlier, one layer deeper and you get more information about features, and one layer before and you get more information about semantics, right? So the input has like a lot of information about the semantics, but no information about features. Then this kind of has less information about semantics, but a little bit more about features, and this has even less about semantics and more about features. So you see that there is some kind of inverse relationship as we go along, and this is why this pathway is called the localization pathway, because in kind of along this line we are just getting like approximately where our features are located, right? So we're kind of localizing them in a very approximate manner, and that's why this is called reconstruction pathway, because now we are really fine tuning these the semantics of our features that we've identified. So let me just point out another subtlety that I think so gets missed. is, yep. So this is concatenation, and let's say that we're concatenating some lower level block with an upper level block. So let this be like the lower level block, and what you can see is that the receptive field size of a pixel over here is much more than a pixel here, right? So because we did a max pooling, and because then did convolutions, you can read up about this if you don't know it. The receptive field size is much larger here. So when we concatenate these two, these blocks have a larger field size. So like one pixel over here would correspond to like a larger region, and one pixel over here would correspond to just a smaller region. So when we take a convolution over these, we're kind of looking at this region with both this. So we're looking at this point in the context of both of these. So this is a better example. So let's try to classify this pixel over here and this one over here. Now these two in a local neighborhood are virtually indistinguishable, right? You cannot tell the cat from the dog. The only way I can look at classify this correctly is that if I look at that in the context of this global feature, right? And similarly over here. So that's why it's really important for the convolution to look at one location in the context of a larger frame, and that's why the difference in receptive field size helps our segmentation task. So this is what is commonly referred to as looking at local features in the context of global features, and you will read this all the time when you read papers, and I have never seen this explained anywhere. As you can imagine that when this happens at all levels, the UNet really gets an in-depth understanding about how an object behaves in every scale of reference, and it understands how to integrate local information with an object's global position, and it also understands when to classify something according to its global position and when to classify something according to its local position. So this really helps it kind of take care of kind of the different variability in object sizes, frames of reference, and angles. All that variability is learned along this pathway. Now let's take a look at how the last layer differs in the case of segmentation. Well, in segmentation it's a bit different. So if you have two classes, you have two filters, right? And so let's say this is the filter associated with class 1. So this filter is going to place itself at every location in this final activation map, and it's going to look through the features look through this entire block for the features that it thinks predict the probability of class 1 being present, right? So at those locations related to those particular features for class 1, it's going to have like positive weights, and it may penalize some features being present by having negative weights or however, and it's going to just place itself at this point and score this point according to the local features that it sees around this, right? And so for here it will get like some probability p, and then it will move across to this point, and now it'll create another scoring. So for every point it's going to score every single point the exact same way, and it's going to output a probability for every single point. So that's how you're going to get this 2D mask like before. And similarly the class 2 filter is going to do exactly the same. It's going to place itself at every point and then look in the neighborhood, in the local region around that point for the features that predict the existence of class 2, and then finally that's going to be another 2D map, and this is generally the output. And finally if we want to know the highest of which class, so you're going to, for every pixel you're going to have a probability of it belonging to class 1 and class 2, and how many ever other classes you have. And then finally you could do like a argmax, or take the class that has the maximum probability at every single index, and that's how you'll finally get your segmentation mask. And so you can see that like in this example, the filter associated with the car had the highest probability and it won over against all the other filters, and in this one it was the person one, and so on. So that's pretty much the UNet. There are some variations that you can do to it, like you can have, as I said, you can have skip connections all the way through. You can do something called deep supervision, which is something you should check out. You can also use a pixel shuffle to upsample and things like that. But basically the entire philosophy of the UNet is this, right? You can use kind of all this lower level information to really get fine grained segmentation, a fine-grained classification of each and every pixel in your input. And sometimes you may see the UNet also like this in papers. This is just a flattened out version of this. So I hope you enjoyed the video. I hope you learned something not just about the UNet but also about segmentation, and really the philosophy and the thinking behind this architecture and what's going on inside. So thank you for watching. Please leave a like and comment and subscribe. Thank you.